Okay, thank you all for coming. I very much appreciate it. I also very much want to say thank you to Miro and Yuri for organizing this. It's very much an honor for me to be here, so thank you for that. I also have to thank, well, I'm not as fluent in Slovak as it looks like here. I had the help of Martin and Eva, who graciously translated my slides for me. So you can read in your language while you tolerate the fact that I cannot speak your language. So hopefully the words convey the message and help you understand what I say also. And I have two computers here so I can see my English version. Okay, so what I'll talk about today is a little bit about who I am and where I'm from, what I do. I'm going to go into this idea of disturbance regimes and lessons we've learned about large disturbances in North America. I'll be talking about ecological forestry approaches that are emerging based on these ideas, and some thoughts on management responses to these large disturbances. Okay, I am a forest scientist. I work for the state of Washington, not Washington, D.C., the other coast in the Pacific Northwest. In fact, this is going to help here. So I'm from over here. I'm also an affiliate professor of forestry and environmental science at the University of Washington. What I study basically what I call chaos in the forest, mayhem, whatever you want to call it. Wind, insects, fire, volcanoes. And I also study how old-growth forests develop, and I relate these two, how different kinds of disturbances generate different successional paths toward old-growth forest. So I do live in Washington State, and that's where much of my work takes place, but I also work all throughout Western North America. So just to show you some idea, I'll take you on a picture tour of the places I work. I'll start on the coast, in the coastal temperate rainforest. So this is a place where it's very wet, because it's on the coast, and we grow very, very big trees. So that's me standing next to a spruce tree. It's a Sitka spruce. This is a western red cedar tree. We also make very giant logs, of course. So, and in this system, disturbances tend to be quite infrequent. They're quite rare. Okay, now I'm moving up into the mountains, the Cascades. We have active volcanoes here. Our ecosystems go from mountain ecosystems all the way to alpine zone. We have a wet side of the mountains and a dry side of the mountains. Disturbances are quite variable here, which I'll talk more about in a minute. But you'll start to recognize some of these genus of trees. It's very similar to European tree genera. Now I'm moving inland on the dry side of the mountains. So now we have a continental climate. It's dry and it's cold. We have a lot of lowland steppe that's not forest, but we also have a lot of dry forest. So these are bison and Yellowstone. This is ponderosa pine forest. And this is a scar on this tree from a fire, which I'll talk more in a second. Did I go too far? Okay, now I'm going to the Rocky Mountains. Here we still have the continental climate. This is the Rocky Mountains are kind of the roof of our continent. The forests range from dry to wet, also montane to alpine, and disturbances are quite variable here. And again, some similarities. And this is a grizzly bear in Yellowstone. One of my favorites, of course. And then another favorite place that I've spent some time working in is Alaska. This is a place where, of course, we have a continental climate with a cold boreal forest, but this is a vast, vast area of very wild lands with very minimal amount of human management. Most disturbances tend to be infrequent. And again, you recognize a similar set of tree genus. So why did I tell you all this? In part so I could show you some nice pictures, but also so you can see how we may be a little bit different where I'm from, but also a little bit similar. And to show you that what I'm going to tell you in this talk it comes from a wide range of forest types, not just one forest type. So I'm going to tell a bit of a story of our evolution of thinking on disturbances, and I'm going to start with fire as an example. Okay, so the story begins with when European Americans settled the west part of the continent in the 19th century. So the landscape they encountered was this huge landscape of primary forests that was largely unmanaged by humans. Native Americans were present, and Native Americans did manage the natural resources, of course, but many of the mountain areas experienced minimal management from Native Americans. So for the most part, natural processes dominated and determined what the forest looked like at that time. So this is really important context that we'll visit on this story. So in the West, we have lots of lightning. And lightning happens when we have very dry summers. So these lightning storms often ignite wildfires. So as a minimum, every year in the US, about 2 million hectares burn in fires. And often it's as high as 30 million hectares. It varies. So the early mindset we had when we settled the West was that fire was bad. Fire was destructive. And we had this idea in our head of a stable landscape that was always covered in mature forest. And we really thought that fires were destruction. And so we began an aggressive policy to suppress all wildfires. And we used airplanes, we used people on the ground, we used bulldozers, tanks, you name it, to extinguish all fires. And here I'm going to show you that it worked. So remember this tree with the scar from the fires? So those fires leave marks in the tree rings. And you'll learn more about tree ring work, I think, from Miro's talk. But if we take a cut from this section and smooth it out, we can see when the tree gets injured by fire, and then later it gets injured again and again. And we can actually date every time this tree burned. And this is a minimum number of times the tree burned, because some fires don't leave scars. But these are the fires that left scars on this tree. So this is the chronologies that are built from here. So I'll walk you through. Each line this way is a tree within a forest stand. And each tick mark is a time that that tree burned. So this tree burned this many times. This tree burned this many times, right? And the point I want to show you is that it worked very well. Fire suppression worked very well. All the trees are recording lots of fires, and then when we started suppressing fires, almost none. So we were very effective at suppressing wildfires. But this was not without a price. This came with a price. So the forests without fires that burned through here and kept this cleared, now we had lots of regeneration coming in and making the forest very dense. And with that, trees that needed lots of light to regenerate declined. With the higher tree density, the drought stress increased. We started to get insect problems. We had some decline in habitat value and also productivity. And of course the fuels built up because they were not burning. And so what happened was, by putting out all the fires that used to look like this, fuels built up. And now the fires burned like that. And so we actually made the fires worse. And we could control these fires, but we cannot control these fires. So we made the problem worse. And this is a problem we're still dealing with today. But we learned our lesson from that. We now know that what used to be considered an enemy, these low surface fires, became actually our friend. And we, instead of putting out fires, we started igniting wildfires. So we have pictures now of Smokey the Bear actually igniting these fires. It's sort of a complicated scenario now, but now we know that putting those fires out has consequences. However, we did still feel that only cool surface fires were okay that did not kill many trees. Big fires that killed trees we still considered evil, bad. So with this idea that when we started to realize that the forest needs a particular kind of disturbance, this idea of a disturbance regime started to emerge in forest ecology. And so this idea that all forests experience disturbance. There's no forests that do not experience disturbance. In fact, every ecosystem. And disturbance regime includes what type of disturbance, how often it happens, how severe it is, how big it is, etc. But I like this, that it depends on disturbance, that the forest needs rain, it needs sun, it needs soil, and it needs disturbance. And I'll revisit that in a minute. So the next part of the story I want to talk about is a series of events that really changed our thinking about disturbance. And the Yellowstone fires of 1988, which many of you I'm sure have heard of, were a very big deal in our country. It was the world's first national park. It's a huge landscape, almost 1 million hectares. It's an icon for America. It's very important. And in 1988, we had an extreme drought. We had several fires start. They all converged into a few very large fires. And we had tons of firefighters, thousands of firefighters, but they made almost no effect. It didn't matter what we tried to do. The fires burned very hot, and they were standard placing. They killed almost all the trees in the places they burned, in most of the areas. So by the time it was done, about 40% of the national park burned. And it looked something like this. And so it was a very dramatic change. And there was a huge amount of attention on this. The Yellowstone fires were initially considered to be a disaster, our park is destroyed, it's ruined. And there was lots of media attention about this and a lot of blaming of people, this is your fault, no, this is your fault. And really that same narrative I told you about the fire suppression and the fuel buildup, this really became a major question. People really thought that the Yellowstone fires were our fault because we had put out fires and let fuels build up. But we now know that that is not the case. That is not the case. Those fires were driven by extreme weather events, not by the fuels in the forest. So it's widely recognized now that forest management actually did not cause the way that the Yellowstone fires burned. Those forests were old, and it's in a forest type that was ready to burn and to cycle back to young forests. And how do I know that? It's kind of a bold statement. Because of tree ring work. That actually a colleague of mine, Bill Rami, did this work where he says basically, from the tree rings tell a story that Yellowstone forests burned every 3 or 4 centuries, every 300 to 400 years. And when they did, huge areas burned, and they burned severely. It killed all the trees and generated new forests. And the Yellowstone landscape has been cycling through fires like this forever. The other thing about the Yellowstone fires is that the recovery was surprisingly rapid. It was very robust. Immediately following the fire, there was a carpet of seedlings in most areas. And this is now about 20 years later. It's quite dense, new young forest in most areas. And oh yeah, and that was without any planting or management, because this is a national park, so we don't do that there, which I will revisit again. And I just like this picture of a colleague of mine just sort of swimming in a sea of trees. It's a very dense regeneration. So this is a graph from Monica Turner's group about Yellowstone regeneration density. And the main thing I want to draw your attention to is the tree density here, the mean values. 60 or 70,000 trees per hectare. That is an enormous number, extremely dense. This is the mean value. There were some that were down here and some that were over 100,000. But the message is that there was regeneration, it was abundant. And the reason is, one reason is that Pinus contorta, lodgepole pine, it's adapted to severe fire. When it burns and gets hot, the cones open. The cones stay closed until they burn, then they open in the heat. And so then the seeds get released into the burned landscape. So it's an adaptation to severe fire. Sort of another sign that this landscape was adapted to fire. And this comes from a whole series of papers from another colleague of mine, Monica Turner's group, largely led this along with Bill Rami. I thought this quote was kind of summed it up. They found that natural processes restored the vegetation cover quite rapidly, with very few or no negative consequences observed. So this was totally opposite of what everyone expected when Yellowstone burned. And so it was not so destroyed. So the next question we had, in Yellowstone we experienced fires, but we also experienced bark beetle outbreaks. Just like you have spruce beetles here, the Ips typographus, we have Dendroctonus ponderosae, similar. It kills large swaths of trees. And the question was, do beetles result in more severe fires? This is a huge question in the US because we have a lot of fires. And so you're looking at some work that we did from the Yellowstone area. These are measurements of beetle kill intensity. These are measures of fire severity. And you can see there's no relationship. It's just like a shotgun blast, a scatter of points. Basically beetles had no effect on how severely the forest burned, which was also a surprise. We thought that the generation of all that dead material would result in more severe fires, but it did not. So to sum that up, the Yellowstone fires were not an ecological disaster as it was expected. That these fires are natural behavior for this ecosystem, and that the recovery processes have been quite rapid, robust, and diverse. So this is the second lesson we learned, that not only are those cool surface fires important, but even these large, severe fires are actually important. And Yellowstone was just one example, but there are many others that happened. Yellowstone was the most symbolic of this. A wide range of fire types is now recognized, and that some systems are quite well adapted to severe disturbances. And in fact, many systems actually need and thrive on these disturbances. And this is also not just limited to Yellowstone. This is something we found in coastal temperate rainforests. It's something we see in the boreal, and it's something we see in other subalpine forests. Okay, the next thing I want to talk about is how variable disturbances can be, even large ones, and why this is important. So in our country, a lot of people have described forests who have gone through a disturbance like a beetle or wind or fire as that it creates a moonscape. It's destroyed and there's nothing there. And I've been on places that are like a moonscape. This is in Hawaii on an active volcano. There's nothing growing here. But fires and other disturbances are totally different. There's actually quite a few things here. The big burn patch there. This is all inside a wildfire. But you can see it's very patchy. So here's an example, again, the Yellowstone fires that Monica Turner's group did. I kind of repeated this analysis for the Biscuit Fire in Oregon, which is related to my dissertation work. It shows that if you look at this map, we have distance to surviving trees. These are the live trees in the green. And this yellow is very close to the green. And the red is very distant from the green. So most of the areas that burned very severely here are yellow, meaning that most of the area of the burn was close to live trees. And these presented an important seed source. So here we go, where this is just a graphical version of the same data. And this is Monica Turner's graph that shows the area of the fire here and the distance from live trees. And you can see that most of the fire area was actually quite close to live trees. And I found a very similar thing on the Biscuit Fire. And incidentally, this is about how far tree seeds fly. So this is a very important source for tree regeneration, is these islands of leaf trees. Also want to talk that this is not just limited to fire, so now I'm going to branch out into other disturbances more. So like you guys with the spruce beetle, we also have our own bark beetle issue. So we've had 10 million hectares in the last couple decades. It's a huge area in Canada and also the US. And this is one example from the Rocky Mountains, from the Absaroka Mountains. This is the Douglas fir beetle, which I've studied quite a lot. And you can see it, you're probably very familiar with what some of these beetle kill areas look like. In our part of the world, beetles cause partial mortality of the stand. So we tend to have, you can see this is years since disturbance, proportion of basal area killed. Almost all of our disturbed stands are between about 40 and 80%. Just about all of them in multiple forest types. So for us, this is very, very common. Many studies have shown this, and I've been surprised to come here and see that the European spruce beetle tends to be closer to 100%. It's a little bit different than ours. But it's interesting to see what this looks like. This is also Douglas fir beetle in the Yellowstone area. It's very mixed, live and dead. And this is from the mountain pine beetle, also from the Yellowstone area. And you can see it leaves lots of live trees, a mix of green and dead trees. And also windstorms. This is from the Olympic Peninsula in Washington State, showing once again that there's surviving trees scattered throughout the wind patch and also around the wind patch. Okay, this was my first appearance in the journal literature as a young technician when I was like 20 years old. This is from a study I worked with Bill Keaton and Jerry Franklin, where they studied the effect of these trees that survived the past disturbance. So again, those surviving green trees and how important they were. So with those live trees, there was high regeneration density. Without, there was much lower. And these were in forests that were now 150 years later since the disturbance. And 150 years later, it still made a difference. So they concluded that it really accelerates the successional rate of these forests to have these live trees that remain after disturbance. So the third lesson we learned is that even large severe disturbances do not homogenize the landscape. In fact, they're an agent of heterogeneity. They diversify the landscape. Despite a visual impression of disaster, they're really not. And so surviving trees are really important. And this is an example from the landscape I worked in for my PhD work. You can see patches of old disturbances there. Create some different patches on the landscape. Okay, the next really important event that we had, although it was around a similar time in the 1980s, was when Mount St. Helens erupted. So I was 4 years old when Mount St. Helens erupted, and I remember shoveling ash from my driveway. So I lived very close, and it really was. It looked like a disaster. I mean, it really did look like a moonscape when it first went up. I had no idea I would be studying it, but. It leveled a large area, but once again, ecologists were surprised, and foresters were surprised at how fast that landscape regenerated. You can see here we're getting tall trees here. This is about 20 years later. We have a diversity of vegetation, not just trees, but also herbs and shrubs. And we had wide variations, everything from very, very dense regeneration to scattered and sparse regeneration. So we had a lot of diversity in the landscape. And the real lesson that came from Mount St. Helens was this one of legacies. And maybe many of you have heard of legacies after disturbance. But this is really where this concept came from Dr. Jerry Franklin. And they found that this dead wood and other structures was really critical to the way this landscape regenerated. So it created habitat for small animals. The animals spread seeds of the plants around, turned over the soil, and this aided regeneration. It actually went faster. And it was not a connection that we had really made before. And again, this is a whole series of scientific papers on this topic that came out. So this lesson was fairly simple. Our fourth lesson was that pretty much every disturbance leaves legacies. And it's what defines secondary succession. And that these legacies are really important. Having these structures there is really important for the way these systems respond to disturbance. Okay, so next I want to talk about what we call early seral ecosystems. What are these? These are the systems that are created after a disturbance, but before the tree canopy recloses again. And you can see in the background here that it's this system here with the remnants of the past stand and the new regenerating stand. So one thing that we've been finding is that regeneration after these disturbances of all kinds tends to be actually fairly slow. And so it's not like we have a disturbance and immediately the forest regenerates to tree cover. There's a period that can last maybe 25 years before the trees are done regenerating. And here, actually, it can be up to 50 years before the tree cover closes again. So there's this whole period that's created before the tree cover closes that is now kind of the focus of quite a lot of attention. So I've been involved in some of these ideas. We're starting to collect some data on these systems. There's a new level of interest in them, and this is kind of our old model. We thought that old forests tend to be complex, and that when they're disturbed, the system is simplified, and that it does not have the same value in terms of structural complexity as do old forests. And this is the classic model. The problem is this is old thinking. And it's thinking that's based largely on models of forest management in managed forests, where we really did simplify young stands. You can see there's none of that legacy here of dead snags and logs. There's no live trees in there. And there's only one species growing there, and it's a tree. That's it, for the most part. So this is sort of old thinking. And I show this picture because it really demonstrates the variety that's out there. So this is the same hill slope after the same disturbance event, right next to each other. So this has been cleared, salvaged, and planted, and this has been just allowed to develop naturally. And my point here is that they're very different. These young ecosystems can look very different. And so now it's starting to be recognized with updated thinking that actually there's quite a bit of structural complexity in these young stands. And in some ways they might be somewhat similar to old stands in terms of the habitat value they provide and things like this. So this is things I borrowed from Jerry Franklin and Norm Johnson. So these are some recognized attributes of young early seral forests. That they have different microclimates, they are structurally rich, they're rich in biodiversity, with some species actually depending only on this kind of forest. They can't live in a closed forest. Functionally rich, and actually now we're starting to think that they're artificially rare. So we know that historically we had more old growth and now we have less old growth because we cut it. But we also realize now that we used to have more natural early seral forests, young forests, and now we have less of that because we have intensively managed the landscape and we've created mostly plantations and mature forests. So we're missing both old and natural young forests. And these are just some pictures of what they look like with the different regeneration components and legacies. This is after a wildfire in the state of Oregon. And one thing that's starting to also be really appreciated about these is that these systems are really important habitat for wildlife. So as a hunter myself, I appreciate that this is where I find deer and elk. That's well known. It's also important habitat for certain species of birds and amphibians and quite a number of species actually, and there's a lot of studies that are starting to show this more. And in fact, it's been known for a little while, so this is with successional stage and mammal species richness, that this young stage, before it gets to the closed forest, is the most diverse in terms of number of species for some groups. So I have to throw in a caveat that my message doesn't apply everywhere. There are forests that are not so resilient. Some forests are not so resilient to disturbance. And there's forests that are really adapted to the low severity disturbance that do not kill many trees. And so if a big disturbance happens there, the forest is less resilient. And especially in areas like this is data I have from these sites where that barely support forests. They're marginal. They're right next to grassland. And this is 25 years after a different section of the Yellowstone fires, actually. And we took data here, and there's still no trees regenerating. And this is especially important with climate change. That if things are getting warmer and drier and less stable, that some forests may not regenerate. So I just want to throw that caveat in there. So now I'm going to update this disturbance regime concept to talk about scale. So you're looking at a graph here with the size of disturbance and how frequent those disturbances occur. And you can see that small disturbances like endemic beetles and tree fall gaps, they're very common. They happen very frequently. But we have this curve that comes here through most disturbances that we know. And then out here at the tail are these very rare large disturbances that are so rare we know them by name. We know what we mean when we say the Yellowstone fires, Mount St. Helens. Is it Kirill? Is that how you say that? Yeah. We know that one by name because it was such a huge event. But we also know that these are part of the disturbance regime. They're rare, but they happen. They only seem rare to us because of our short lifespan. So now, moving on from these down to here. So now, if we manage forests with only those small events in mind, like managing to mimic tree fall gaps and that kind of thing, or cool fires, we're actually missing part of the way that this system functions. And that this idea that we can maintain a stable forest cover on a landscape forever, always, is really a dead idea. We know that landscapes are dynamic, they're always turning over. We're going to see patches of disturbances all the time. Basically, this is a quote I found that sort of attributed our initial problem with disturbance, or our notion that disturbance is bad, to our European heritage. I found this, I thought it was interesting. Okay, now I'm going to move to talk about management. So what does this kind of thing mean for management? So there's an emerging idea of ecological forestry. This is starting to catch on a bit in my country, as well as a few others. These are based on largely the thinking of Jerry Franklin and also Norm Johnson. They published a few papers on these ideas. And the idea is really that to imitate the full range of natural disturbances. So it includes preserving and developing old growth, but it also has variable retention harvests to mimic large disturbances. So not be afraid of creating openings. It allows early sterile communities to persist. So to do this, it avoids aggressive tree planting, site preparation, and vegetation control. It kind of just lets the system close the canopy on its own. It might take a few decades. And the real key is to maintain the representation of all the sterile stages on the landscape, not just mature forest. Here's an example. Actually, the agency I work for, the Washington DNR, we actually do some of these approaches where instead of just a simple, clean clear cut, which is what we used to do, which was just nothing in it, now it's more complicated. It's been called a messy clear cut by some people, where we leave these stringers and patches of live trees, and also on the ground there's dead wood. And here's a few other examples of that. And the real idea is that it's meant to mimic that fire pattern that I showed you, or other disturbances. So these are really sort of pattern after natural disturbance regimes. So it's, the idea is managing with the disturbance. So the public response to this new approach has not always been so great. So they like to joke that it's like an angry mob coming after them, and that it comes from all directions. That environmental groups tend not to like it because they just think it's a clear cut, and I hate clear cuts, so it's bad. That's kind of the mindset there. Industry has said that basically we won't have the same amount of wood supply. This is a less productive way to produce wood. And the foresters basically see that diverse early sterile stage before tree cover as wasted time. That we're failing to recover the site. However, some people are starting to come around to the idea, and it is catching on, and it's actually being implemented in some areas. Okay, so now as part of this sort of ecological forestry approach, I might talk a little bit about post-disturbance management. As many of you know, I have a little bit of experience with the salvage logging issue. I won't really dwell on that experience, but I'm happy to talk about it if you would like to afterward. But it really comes down to a lot of this issue comes down to salvage logging. And now I want to bring us back to this beginning of the story, because this is very important context. So remember, we encountered ecosystems back just 150 to 200 years ago, not very long. These were vast landscapes of primary forests. And so we have this different perspective than in Europe. And we know that these landscapes now, they experience thousands and thousands of years of fires, windstorms, bark beetles, volcanoes, whatever. And cycles of these. But when we came there, the forests were still there, without being managed, by and large. So that's really important context. So in some landscapes then, there's not really an urgency to salvage log or plant or actively restore or recover disturbed sites. And it really comes down to pre-disturbance objectives. It's actually fairly simple. In commodity landscapes that are managed for timber production, for wood, for money, economics, if it burns or has a beetle outbreak, we salvage log it. because the objectives for that piece of ground was to manage for economic production. So we gather the wood. We also have mixed forest landscapes called national forests that are managed for both economic and ecological reasons. It's a little bit of a debate there, but lately, more often than not, we do not salvage because the ecological effects are deemed to outweigh the economic effects. By and large, that's been the case lately. In national parks and wildernesses, it's a never. We just never salvage. It never happens because it's really about natural processes. And so I want to visit that a little bit more. Why don't we salvage in our national parks? It's because our objective for that landscape is not about preserving a static forest cover. It's about allowing natural processes to operate freely. That's what the public values in national parks, in part. We also view those natural disturbed forests as natural laboratories, learning opportunities, basically. We can understand about how forests are responding to climate change, which is very important. Forests are changing with climate change. We can develop improved silvicultural regimes as we learn more about disturbances, like the ones I showed you. And it's basically thought that if we go in and actively manage, that opportunity is lost forever, and there's no going back. We also do it for biodiversity and to have a diverse landscape. And by having that diverse landscape, it actually can affect the spread of future disturbances. And like I said, we come from a history that shows that the ecosystems don't necessarily need us to respond to these disturbances. Okay, so now to conclude. Basically, this approach worries about forests less. So I always like to say that people worry about forests a lot. And most of the time, forests are okay, no matter what happens to them, right? So, and in a national park, we just don't worry about the forest. It just does its thing, right? And so, and ecological forestry would not even happen in a national park because we don't manage it all. Other than preservation. On mixed-use lands, we would implement ecological forestry, and we might do cuts like this. And we would also allow natural disturbances mostly to do their own thing. And the idea here is that we're not aggressively planting trees everywhere. We're okay with there being a period where there's no trees in the site, or very few trees. And it's dominated by other vegetation. So under ecological forestry, that's an accepted thing because we recognize that under the natural disturbance regime, there were times when the land was not dominated by trees in some areas. So it's basically not only accepted but encouraged. So in the context of Haithathras, we would probably not plant those sites. They probably wouldn't have been salvaged, but if they were, we probably, under this management scenario, we would not plant.